Welcome to Beyond the Brackets. In today's video, we'll be solving homogeneous system of linear equations. An equation of this form, where xi's are unknowns and ai's are constants, is called a linear equation with n unknowns. For example, 2x plus 5y minus 2z is equal to 0 is a single linear equation. When we have more than one such equation involving the same variables, it forms a system of homogeneous linear equation. This system can be expressed in the matrix form as Ax is equal to 0, where matrix A represents the coefficient matrix containing the coefficients of x, y, and z, wherein the first row contains the coefficients of x, y, and z from first equation, second row has coefficients of x, y, z from the second equation, and third row has coefficients of x, y, z from the third equation. Matrix X represents the column matrix of variables. Here they are x, y, and z, and then the zero matrix which has zeros from the right hand side. We know that a system of equations is said to be consistent if it has at least one solution. In case of homogeneous system of linear equations, the values x is equal to 0, y is equal to 0, and z is equal to 0 will always satisfy the equations. So this is called zero solution or trivial solution, and it is always a solution for every homogeneous system of linear equations. So, since the zero solution always exists, a homogeneous system of linear equation is always consistent. A homogeneous system of equations, Ax is equal to 0, has a unique solution, that is zero solution, when the rank of A is equal to the number of unknowns. On the other hand, if the rank of A is less than the number of unknowns, then the system has infinitely many solutions called non-zero solutions. Let's proceed to solve the first question. We are asked to solve a system of equation. If you observe carefully, the right hand side, the constant term is 0 in all the equations. That tells us this is a homogeneous system of linear equation. As usual, we first form the coefficient matrix capital A and the variable matrix X. Now we'll reduce the coefficient matrix A into echelon form to analyze the system and find the solutions. We'll make the first element as 1 by interchanging R1 and R3. Next, we'll make these elements as 0 using R1. So the operation will be changing R2 as R2 minus 3R1 and R3 as R3 minus 2R1. After the first row is written, for the second row we get 3 minus 3, 2 plus 12, 1 minus 15. For the third row, 2 minus 2, minus 1 plus 8, 3 minus 10. This 14 and 7 common in root 2 and root 3. We first simplify that before moving on to the next step. For the next step, we got to make these element as 0 using R2. So the operation will be changing R3 as R3 minus R2. After the first two rows are written as it is, for the third row we get 0 minus 0, 1 minus 1, minus 1 plus 1. Here rank of A is 2, which will denote by R. The number of unknowns or n is 3. So the system will have n minus r, that is 3 minus 2, which is one linearly independent solution. Remember that if the system has non-zero solution, we call it as linearly independent solution. If the system has zero solution, then it's called linearly dependent solution. So non-zero means independent, zero means dependent. To find the linearly independent solution, we'll write the variables from the resultant matrix. From that we get two equations, x minus 4y plus 5z is equal to 0 and y minus z is equal to 0. Since there are three unknowns and only two equations, we'll have to assign a value to one variable. Notice that y and z are common in both the equations, so we can assign a value either to y or to z. Let's take z is equal to k. From the second equation, since y minus z is equal to 0, we get y is equal to k. Substituting these values in first equation, we get x is equal to minus k. So the values are x is equal to minus k, y is equal to k, z is equal to k. Taking k common from all these equations, we get x is equal to minus 1, y is equal to 1, and z is equal to 1. So minus 1, 1, 1 is the linearly independent solution. Moving on to the next problem, we are asked to find the solution of the system of equations. Here we have four equations, x, y, z, and omega. First, we write the coefficient matrix, matrix A, which contains all the coefficients of the variables, and variable matrix X, which contains the unknowns. We start by reducing A to echelon form, wherein these elements will be made 0 using R1. So the operation will be changing R3 as R3 minus R1, R4 as R4 minus R1. After writing the first two rows, for the third row we get 1 minus 1, 1 minus 1, 1 minus 0, 1 minus 1. For the fourth row, 1 minus 1, 1 minus 1, 2 minus 0, 0 minus 1. Next step is to make this element as 0 using R3. So the operation will be changing R4 as R4 minus 2R3. After writing the first three rows, for the fourth row we get 0 minus 0, 0 minus 0, 2 minus 2, minus 1 minus 0. The matrix is now reduced to echelon form. Since there are 4 non-zero rows, the rank of A is equal to 4. We also know that there are 4 unknowns x, y, z and omega. So the system has n minus r, that is 4 minus 4, which is equal to 0 linearly independent solution. That means there is no non-zero solution. So the only possible solution is x is equal to y is equal to z is equal to omega is equal to 0. Let's look at the last problem. This is a homogeneous system of linear equations with 3 variables x, y and z. If the system has only 0 solution, then there's nothing much to prove. So our goal is to find the values of k for which the system has non-zero solutions. We know that a homogeneous system has non-zero solutions if the rank of A is less than the number of unknowns. That means rank of A should be less than 3. Now the rank of A will be less than 3 if A is a singular matrix. So the coefficient matrix must be singular for the system to have non-zero solutions. Before we find the determinant of the matrix, let's first simplify the matrix to make our calculation easier. To do that, we'll first interchange R1 and R2. Then these two elements are made 0 using R1. So the operation will be changing R2 as R2 minus 2R1 and R3 as R3 minus R1. After writing the first row, for the second row we get 2 minus 2, 3k minus 2k minus 8, 3k minus 8k minus 4. For the third row we get 1 minus 1, 2k minus k, 2 minus 4, 3k minus 4k, 4 minus 2. Since the rank of this matrix should be less than 3, that means the determinant of A must be equal to 0. When we calculate the determinant, we get two values of k is equal to plus 2 and k is equal to minus 2. Let's find the non-zero solution of this system when k is equal to 2. So for the matrix A, we'll substitute 2 in place of k and this gives the new matrix for A. Now we'll reduce this matrix to the echelon form. To do that, we first divide R1 by 2 and this is the resultant matrix. Next, changing R2 as R2 minus R1 and R3 as R3 minus R1. First row will be written as it is. For the second row we get 1 minus 1, 6 minus 3, 10 minus 5. For the third row we get 1 minus 1, 6 minus 3 and 10 minus 5. Next, making this element as 0 using R2. So the operation will be changing R3 as R3 minus R2 after writing the first two rows as it is. For the third row we get 0 minus 0, 3 minus 3, 5 minus 5. The matrix is now reduced in the echelon form. As you can see, there are two non-zero rows. So the rank of A denoted by R is 2. We also know that there are three unknowns x, y, z. So the system has n minus r, that is 3 minus 2, which is equal to 1 linearly independent solution. Now let's find the solution from the resultant matrix. We get the equations x plus 3y plus 5z is equal to 0, 3y plus 5z is equal to 0. Since there are three unknowns and only two equations, we need to assume a value for one variable. Y and z are common in both the equations, so it will be either y or z. Let's take z is equal to k. Substituting this in equation, we get y is equal to minus 5k by 3. Substituting y and z in equation 1, we get x is equal to 0. So the values of x, y, z are 0, minus 5k by 3 and k. Taking k common, we get 0, minus 5 by 3, 1. Since we don't want fractions in the final answer, so taking 3 outside, we get 0, minus 5 and 3 as the final answer. Doing the same process for k is equal to minus 2, we get matrix A as shown here. First we divide first row by 2, which gives this as the resultant matrix. While reducing this matrix in the echelon form, the first operation will be changing R2 as R2 minus R1, R3 as R3 minus R1. The first row remains the same. For the second row we get 1 minus 1, 3 plus 2, minus 6 plus 1. For the third row, 1 minus 1, minus 2 plus 3, minus 2 plus 1. Step is to make this element as 0 using R2. So the operation will be changing R3 as 5 R3 minus R2. After the first two rows are written as it is, for the third row we get 0 minus 0, 5 minus 5, minus 5 plus 5. Here the rank of this matrix is 2 because it has two non-zero rows. So the system has n minus r, that is one linearly independent solution. Writing the equations from the resultant matrix, we get x minus 3y minus z equal to 0 and 5y minus 5z equal to 0. From the second equation, we can see that y is equal to z. Since there are two equations and three unknowns, we'll need to assign a value to one of the variables. Let's take y is equal to k. Substituting this in equation 2, we get z is equal to k. Substituting these two values in equation 1, we get x is equal to 4k. So the solution is 4k, k and k. Taking k common, the solution is 4, 1 and 1. I have included some more problems for you to practice along with your solutions. Try solving them on your own first and then check your answers to see how well you have understood the concept.